Good afternoon, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. Hope that you all are doing well and having a wonderful week so far. This is a recording that you are listening in on right now, and the reason for that is because unfortunately earlier today we had some technical difficulties for the webinar, and we have resolved them, and so I am now re-recording the webinar, and this will be sent out to you. And if you would like a copy of my presentation, please email me directly at benkeiser@aft.com. That's ben.keiser@aft.com. Okay, so I'm going to go ahead and get into things, and before we get started, I want to announce a very special piece of information, and that is that our brand new Automated Network Sizing Module, ANS, is now available for AFT Fathom. What the ANS module will do is it will automatically meet your design requirements by sizing pipes in order to minimize your cost or perhaps your piping weight. And minimizing cost can be either in terms of initial costs or life cycle cost. The ANS module contains the incredibly powerful capabilities that have been available in AFT Mercury and AFT Titan for about 15-20 years. And we have improved them, streamlined the capabilities, and integrated them directly into AFT Fathom as a brand new add-on module. So the capability will be much easier to use right in AFT Fathom itself. Very soon, the AFT Aero ANS module will be available as well. And right now, we're doing a very special introductory promotion where if you purchase the ANS module before October 31st, 2019, you'll be able to purchase it for 50% off. So a wonderful discount to get things started. And if you're interested in it, please give us a call. We'll be happy to let you try it out and give you some information and enjoy working with the module. All right, as we get started here, there are a couple of boilerplate slides, and one of the first ones I'm going to skip basically talks about all of our various AFT products that we have available. I'm not going to go over that. If you go to the products menu on our website, aft.com, on the software overview, this is where you can find all of our different software products and then learn more information about each of them. So I'm going to move the website out of the way now, and I'm going to get into the meat and potatoes of today's webinar. What I'm going to talk about today is what do we really mean by the word transient analysis, and how to know which analysis tool is the proper one for the proper type of transient that you want to do. And as mentioned, these are the boilerplate bullet points that I'm going to skip past. It just documents all of our different software products. And again, you can read about each of those on our website. So last time on AFT, just like the previous episode of your favorite TV show, that's how that was supposed to sound, is I did a webinar on May 1st, 2019, where we introduced the AFT Fathom XTS module for doing a transient analysis. You can view that webinar by clicking on the View Here button. If you email me, the presentation will take you directly to that link. You can also find it on our webinar library as well. And so if you watch that webinar, it'll give you a good introduction to the AFT Fathom XTS module and how you can use it. And so that was a good precursor to set us up for today's content. And what I talked about last time was how to get away from using Excel spreadsheets for doing your flow calculations and piping systems. The thing is, I illustrated a very simple fluids textbook problem. And the reason why, if you watch that webinar, you'll learn why I was feeling a little nostalgic. And I dusted off my old fluids textbooks from college. I pulled out this example and I built my own spreadsheet to calculate the pump discharge pressure. And then I built the same model in Fathom and I compared the results and they were the same. But The thing is, the textbook example simply asks, what is the pump discharge pressure? It gives you the known flow rate of the piping system and the pipe diameter. You have to calculate what the pump discharge pressure is, which is pretty easy to do in a spreadsheet. But when you start asking other questions like what's the pump NPSH, how much power is it drawing, what if you start doing different scenarios, then trying to attack that with a spreadsheet or simple hand calculations is very difficult to do, and AFT Fathom works a lot better for that. What I then did was, for the oil tanker example that I initially demonstrated with a spreadsheet and AFT Fathom, is I did a quick transient analysis of that system using the AFT Fathom XTS module. All it was to calculate how long it took for the oil tanker to unload all of the oil into the storage tank. And so that was a very simple question to answer with the XTS module. Next, after that, I brought up a bit more of a complicated multi-tank filling application example, and I demonstrated that in AFT Fathom and did a transient analysis, and I'm actually going to revisit that today, and that's going to serve as the starting point for today's webinar. So here's what we're talking about. Today, the main goal that I'm going to address is, what do we mean by the words transient analysis? There are different types of transient analysis that you can do. And when you ask, does your software do transient analysis? It depends on what you're talking about. And so today's discussion will very clearly identify the different types of transient analysis that you can do and which tool that you would need for each of those different types. So in order to go over that information, we're going to talk about the difference between AFT Fathom XTS module and AFT Impulse. In order to better understand the differences between the different types of transient simulation is to think long-term or short-term, and we'll discuss what that means here in a little bit. We'll go through some various AFT Fathom XTS applications that you might run across. Then we'll talk about some AFT Impulse applications. And then we're going to come back to that multi-reservoir application example from the previous webinar, and we're going to start off with the Fathom XTS module, and then I'll talk about how you can import your Fathom model directly into AFT Impulse. It's a major time saver. That way you don't have to rebuild the model again from scratch. And then we'll go through a a waterhammer or a surge analysis with AFT Impulse for the same system. So getting into this, what's the difference between Fathom XTS and Impulse? Well, this is what you'll see when you first launch the AFT Fathom software. When you launch the AFT Fathom software, you'll find that there are several add-on modules that you can activate. And if you have a license for them, you can use and enjoy those expanded capabilities. And the module that we're going to be talking about today is the XTS module. That stands for Extended Time Simulation. So that's one way of doing a transient analysis right within AFT Fathom itself. Next, we have AFT Impulse. If you were to run AFT Impulse, this is the very first window that you would see when you first go to run the software. So you can do your transient analysis in two different ways. As you are probably familiar, Fathom is a steady state flow modeling tool until you activate the XTS module. Impulse is all about doing a transient analysis. Impulse does have the ability to do some steady state calculations, but those are typically for establishing the initial conditions to perform a waterhammer analysis. So the question is, how are those two transient flow analysis options different from each other? Okay, so the first way to figure out how these two applications are different from each other is to think of a long-term transient simulation versus a short-term transient simulation. When we're talking about the context of the XTS module for AFT Fathom, that's going to be more of a long-term transient simulation. What I'm talking about is you're going to be looking at what's going on in the system for several minutes, hours, even days, and you're going to be looking at more of a macro level of what's going on inside of your piping system as things change. Perhaps you have pumps that are simply changing from one particular pump speed to another pump speed, or maybe you have several different flow demands that are changing throughout the day. As your flow demand changes, you might want to see how your pump is going to change its operation on its pump curve. And you would look at longer periods of time. Those are the types of things that you would see or that you would look at with AFT Fathom XTS. And that's going to become a lot more clear when I get into the example here in a little bit. A key assumption when you're dealing with the AFT Fathom XTS module is that each time step during your transient analysis is at a steady state operation. And so if you have a simulation where you want to see what's happening in a piping network for 2 hours, and you define a time step of a minute or maybe every 2 minutes, well, when you transition from one time step to another, as things are changing throughout your piping network, then the system is changing so slowly where any pressure or velocity surge waves would be fully dampened out by that point. So that's a very valid assumption for each time step being at a steady state when you're looking at longer periods of time with relatively larger time steps. So that's kind of the time scale that you're working with in AFT Fathom XTS. Now, when you're dealing with AFT Impulse, it's a different type of transient simulation. You're looking at a very small window in time. So XTS looks at very long periods of time. Impulse looks at what's happening essentially instantaneously at a certain moment. So let's say that you have a sudden valve closure or a pump that all of a sudden trips as an accident type of scenario, perhaps. Then you're looking at a very short window to see what's going to happen within that time frame. And your simulation periods with AFT Impulse are going to be really short. Typically, you're only going to be looking at several seconds after a valve closure or maybe a pump trip. You might look at a minute or two or a few minutes at most, but in AFT Impulse, your transient simulation periods are not going to be very long. They're going to be a lot shorter. And the reason for that is because Impulse is going to capture what happens after a sudden surge event. Why do you need that? Well, there are several different types of disasters that you could potentially encounter under a surge event. Pipes can rupture or they could collapse. You might run into a low pressure situation where the atmospheric pressure is greater than the pressure inside of your pipes, and that can cause your pipes to collapse. If you have a pump that trips, maybe there's cavitation in your system that's going on. And so in those types of surge events, that's where you need a tool that will handle that type of phenomenon. And the reason why AFT Impulse is needed for doing that surge analysis is because the wave speed is a really important parameter to determine how fast a sudden pressure surge will pass through a system. So let's say that you have a valve that all of a sudden slams shut or it closes. Well, initially you have a velocity of fluid through that valve, and then once that valve closes, that fluid has nowhere to go. And so the pressure is going to spike up and increase at the valve. And just like a traffic jam, where the first few cars in a traffic jam come to a sudden stop, and then all of a sudden the traffic gets all backed up and everybody else has to slow down, it's the same thing here. The entire fluid inside the pipe does not stop flowing at the same time. and you have a pressure surge that passes and communicates back through the rest of the system. That's what impulse is going to do for you. So overall, the two different tools that you can use for handling transient analyses are AFT Fathoms XTS module and AFT Impulse. So again, in summary, Fathom handles slow transients. This is a screenshot of the transient control window, and this is simply where you would define in Fathom XTS how long you're going to run your analysis. So this is that 2-hour time period that I was talking about, and the time step we have defined as being 1 minute. So there's going to be 120 time steps, 1 minute apart from each other. On the other hand, AFT Impulse is doing fast transients, and my simulation time period might be 10 seconds. I have a sudden valve closure, and I want to see what's going to happen in the first 10 seconds. As you notice, the time step is much, much smaller for AFT Impulse. It's on the order of milliseconds. And you're going to have a lot more data points in Impulse that you will with the Fathom XTS module. The reason why is because the wave speed for a piping system is typically several thousand feet per second. So if you have a sudden pressure surge, the amount of time that it takes for that pressure wave to pass through the system is very, very quick. And so you have to have a very short time frame and time step to be able to really capture what's going on. Hang on 1 second. Excuse me. Okay. So that's how AFT Impulse is different, especially with the time scale right there. All right, let's talk about some situations that you would use the XTS module for AFT Fathom. What you're typically wanting to do is seeing how the system changes over long periods of time. How do control valves respond when you're changing from one operation to another? So let's say that you're draining a tank over time. Well, your control valve is trying to maintain a specific set point. So as your tank drains, that control valve is going to respond by opening or closing in order to keep maintaining the same set point in your system. And so one thing that you might want to look at is in XTS, how does your control valve change its open percentage during a transient? Another type of application you would look at is if you have pumps operating on their curves. When your flow demands change throughout the day, you can see how that changes. You might have pumps that are turning on and off based upon different conditions. So if you have a really high liquid height and you're trying to get a lot of flow in a system, maybe you have multiple pumps in parallel that are operating together. And then once your liquid height on the supply gets to be lower than a certain value, maybe you have logic built in that turns off one of the pumps. And that's the type of transient that you can look at with XTS, is how your pumps are changing throughout the day at a larger scale. So just some other things that you can consider when doing a XTS analysis. Another example is what causes a valve to close. Let's say that you have logic built in to close a valve for two different situations. One reason to close a valve might be because you don't want a tank to overfill. That could be one reason why you close the valve. Another reason is maybe you get a certain tank height that you actually need. XTS will help you figure out the reasons why that would happen. Some questions that you would ask with AFT Impulse, again, you're considering very short periods of time. You're trying to analyze a waterhammer situation under a surge event, a sudden valve slam shut. If your valve slams shut, how high does that pressure spike get? If your valve slams shut, do you have cavitation anywhere in the system? When you have cavitation in a piping system, it's like balloons popping inside of your pipes. Definitely do not want to have that happening. And when the balloons pop inside of your pipes, that's going to cause very high pressure spikes. AFT Impulse will be able to help you identify how large those spikes can be. Another application would be what happens to the system pressure if you have a sudden pump trip. So if you have a pump trip, your pressure will decrease, your flow will decrease. How does that affect what's going to go on in your system? How do check valves, relief valves, and other types of valves respond during a sudden event? So if you have a sudden valve closure, maybe you've got some check valves and relief valves that might start chattering or are just trying to relieve flow to different flow paths. That's what you would use impulse for. Are they functioning properly, or again, are they chattering? You definitely don't want them to be chattering. What type of surge suppression equipment do you need? Do you need, gas accumulators, relief valves, surge tanks? Different methods are available to help you protect your system to ensure that you don't have pipes bursting or collapsing. So the time where you would use the XTS module for Fathom is very different from when you use the Impulse software. And they're both tied together. And so the example that I'm going to get into next here is going to illustrate that very clearly on which situation you would use which software tool for. So I'm going to now jump back to the multi-tank filling example that we discussed in the previous webinar. The first scenario that I'm going to go over is just simply filling up the tanks. So here's a screenshot of my system that I'm going to open up here in just a sec. As you can see in my visual report screenshot here, I know the velocities and the flow rates and the diameters and the pipe lengths. This is all the input information with the initial conditions at the very first time step. So initially, my 3 discharge tanks right here are initially empty, okay? This is a tank filling application. So the scenario is to simply fill up the tanks. And the questions that I want to ask, how long does it take to fill up each tank? Do any of the tanks overfill? Because that would be a major problem, especially if it's a corrosive fluid. But even if it's just water, you don't want a whole bunch of water flooding everywhere. And then finally, how does the pump operation change throughout the day? So that is scenario number 1. So let me go ahead and jump back into AFT Fathom here. I've already got the model built, and let me go back to the scenario that is applicable here. So for the tank filling scenario, I have finite tanks model. This is one of the beautiful things about using the XTS module. If you were to click on this button, let me circle it for you. If you were to click on this button just to the left of the status light, this is one of the ways where you can turn on the XTS module. If you turn on the XTS module, it's really useful because when you then go in and open up any of these reservoir junctions, you can then see that there are some additional options available to you. You're not limited to only modeling an infinite reservoir. You can do finite, open, and closed tanks. And this is beautiful because you can then track how your liquid height changes over time during a transient simulation. So in my application here, I have a supply tank. My supply tank is a 40-foot diameter tank, as you can see by the name that I gave it. This is the corresponding cross-sectional area for a 40-foot diameter tank. I have initially 50 feet of liquid head inside the tank. The bottom of the tank is at a 0-foot elevation, so I've got a 50-foot high tank. Those are all my parameters for my supply tank right there. And then I have different discharge tanks here. Each of the different discharge tanks has a different diameter, and they have a different height. So this is a 10-foot tank. This is a 20-foot high tank, but a smaller diameter. And then this is the largest tank height with the medium diameter. And as you notice here, the piping leading to each of the tanks is different. The reason why I wanted to demonstrate this example in the previous webinar and then bring it back today is because this is one of these classic fluids problems, which is really complicated to solve by hand calculation or by spreadsheet. And one of the things that are really important that people care about is a pump and system curve. A pump and system curve is really easy to be able to generate right in Fathom, but there are many times where a pump and system curve is just not even useful at all. And the reason for that is because oftentimes there is not a unique system curve that could even be generated, such as in this application. Since all of these are finite tanks and they're filling up during my transient simulation, the system curve would actually change. So if I have my pump curve right here and then my system curve during the transient, as this tank drains, the liquid height goes down and then the liquid height goes up for my discharge tanks, my static head is going to change as well. So that causes the entire system curve to shift and change over time. So this is a time where pump and system curve is not even useful because it's constantly changing during the transient analysis. So I thought that this was a really good classic fluids problem to show you how easy it is to solve with Fathom. So I'm going to see how long it takes each of those tanks to fill up. My analysis, once I turn on XTS, under the time simulation, I'm doing my transient, I'm doing my transient modeling. And for the transient control, this is where I define how long I'm running the simulation. I want to see what's going to happen in 2 hours. And I'm doing a time step of every 30 seconds. So every half a minute is when I'm getting a data point. So let's go ahead and run the model here and see what happens. Thankfully, it doesn't take too long to run, but depending on what you're doing and how much data that is being taken, you can maybe end up with some lengthier run times when using the XTS module because there's a lot of transient data that it's capturing. Okay, so let's take a look at the output. First question is, when do the valves close? Well, the easiest way to see that is when you go to the output window, simply, I'm sorry, that's not the scenario that we're looking at yet. The question is, we're filling up the tanks. So right now, these valves are staying open the whole time. They're not ever going to close in this particular scenario. So the question is, how long does it take to fill up each tank? Well, there's different ways that you can examine the results. If you're in the output window, which is where all of your output results are stored in tabular format, there's several different fields. There's your piping results, there's junction results, there's junction summaries. Let me break this down really quick here. If you were to look, I'm going to hide the junction section. There's 2 tabs for pipes. There's a pipes tab and there's a transient tab. The pipes tab contains the results for every single pipe at a given time step. So right now, these are the results that you see at time 0. If I was to click on the time scale tool right down here, I can move forward in time and you can see, oops, I didn't mean to erase that. I can move forward in time and you'll see how the results change. So as I go from each 30-second period, you can see how all of the results are updating automatically. This is one way to look at your transient results, not very helpful. Another way is if you were to go to the transient tab for the pipes, right here, this catalogs, again, all the pipes, but it has a little expansion button. So what happens when you click that expansion button, let's look at pipe 2. If I expand that out, this takes a look at all of the transient results for every single time step for pipe 2. So this gives me a little bit better of an indication on how the results change over time for a particular pipe. Still not very useful though on a tabular format, but you can find some utility there. The thing is though, is if I'm looking at the transient tab like this, and I right click on any of these columns, I can do a quick graph, and that will graph how the result changes in that particular column. So that's nice. Next is I have my general section at the top. These summary tabs are component specific results for those types of junctions. So if I want to look at the best efficiency point for a pump, then I want to look at the pump summary, not the junctions down here, because the best efficiency point for a pump means nothing for a valve or a heat exchanger. So results that are specific to those types of components, you're going to find in the general section here at the top in the summary tabs. Again, if you look at just the summary tab, these are the results for all the valves at a given time step. And again, if I keep clicking on the time scale to move this forward, you can see how the results change. So that's just the basic summary tab itself. If you click on the transient tab, you can do the same thing that I show you with the pipes, where you can expand that, and you can see all the transient results for every time step for that particular junction. That brings up my question on how do the liquid heights change in the tanks. So if I go to the reservoir transient tab, I can expand each of these, and then if I right click on the column for liquid height, this tells me how the liquid height changes for my supply tank. If I collapse this and then expand the next one, you can see how your liquid height changes and the discharge tanks accordingly. So that's how the liquid heights change. Another question that I had was, how does the pump operation change? So if I go to the pump transient, I can expand the pump transient data points. I can right click and I can see how the flow rate changes over time. I can see how the proximity to the best efficiency point changes. This is not bad. I'm going from 98% of the BEP down to about 85% of the BEP during this operation. So my pump is still operating really well. And you might also care about the MPSH. So you can look at MPSH results just the same. Now, let's say that I want to take the difference from the MPSH-A and the MPSH-R. Well, the question is, do I have to copy this data and then paste it into Excel? No, there's an output parameter for that. Just like there's an app for that, there's an output parameter for that. So if I open up my output control, this button right here pulls up our output control window. This is where you can specify which types of parameters are displayed for pipes, junctions. These are the summary tabs for pumps, valves, etc. And then there are junction parameters for the transients as well. So if I want to see how the difference in MPSH-A to the MPSH-R changes, I can go to the pump transient tab and simply add the MPSH margin. I can do an absolute or a ratio. Let's add both of them. So if I add the MPSH margin, you can see how the margin changes for the MPSH once I go back to the transient tab right here. So here's my MPSH margin. I've got between 60 and 50 feet of margin, so I've got plenty of MPSH available. That's great. Then you can look at the ratio and see how the ratio changes. So this is good. I've got plenty of MPSH. I'm not going to run into any pump cavitation issues. Now, the best way to really examine your results is by using graphs. So if you go to the graph results tab, This is where you can do all sorts of different types of graphs, especially for transient graphs. So I've already pre-configured several graphs here that I care about. I've added them to my graph list manager. So the reason why that is useful is because I don't have to go back in and reset these parameters every single time. I can just double click on any of these. So the question is, how do the liquid heights change over time? Well, if I double click on that graph, this is what shows me how it does it. So let's take a look at this. I'm plotting the liquid height for these 4 tanks. Now, as you can see, the supply tank continually drops off over time. These 2 tanks are continually filling over time. But look at this one. This one's kind of weird. This yellow graph right here all of a sudden stops filling and then it just levels off. What's happening there? Well, if I uncheck these boxes, it turns off those additional graphs. That way I don't have to delete those parameters. And let's go ahead and turn on the crosshair. We can see here that this is a liquid height of 20 feet. So at 35.5 minutes, this tank, the liquid height reaches the height of the tank. This is a really big problem because what this means is that I'm now overfilling the tank. And this fluid is just draining right out of the tank. Everything is just continually spilling over, not a situation you want to have. So that's where I have scenario number 2. Scenario number 2 is I want to close the valves to prevent overfilling for any of the tanks. So what I have done is for each of these valves, I've defined a transient. So this is for this particular valve right here. So I have an event transient, which I want my valve to close if a certain criteria is met. This tank is a 30-foot high tank. So I've set up criteria to cause my valve to close, which goes from the initial K factor to a K factor of -1. A K factor of -1 represents a closed valve with infinite resistance. And I want that valve to close if the liquid level gets to be too high. So if my liquid height gets to be greater than or equal to 28 feet out of the 30 feet, close the valve. I did a similar thing for the other 2 valves as well. So this one, I told it to close when this tank is up to an 18-foot liquid height. And then this one right here, this is a 10-foot high tank behind the window, and I want that to close at 9 feet. So that's how I set up my transient. The little T here means that you have a transient set for those types of valves. The key thing is, if the reservoir liquid heights, if this criteria is never met, then this transient is never activated and that valve would not close. So the questions here: how long does it take to fill each tank? When do the valves close to prevent overfilling? How does the pump operation change? So time to jump back into Fathom. This is scenario number 2. Close the valves to prevent overfilling the tank. So this is again for my original 2-hour transient simulation. So 120 minutes there. I've got all the things set up. That's the only change I made, was to apply transients to these valves. Let's run the simulation and find out when those valves close. To give you a little answer ahead of time, is what you're going to see is actually only 2 of the valves close in this system during my 2-hour transient simulation. Which valves close? We're going to find that out. And the last simulation that I have is a 3-hour long simulation because I want to find out when all the valves close. All right, I've got some results. Let's take a look at what's going on here. This is just loading the output data for me. Okay, so I can see now that I have some warnings displayed on the warnings tab. They're caution messages. This is not really anything to be worried about. the key thing, without going into a whole bunch of detail about warnings, is read them. Read the warning message and what it says, and then follow the advice right here to hit the F1 button on the keyboard, and that way you can understand what the warning message is telling you. Some can be really problematic, others are just cautionary, so it's important to pay attention and just really read and understand what it's trying to tell you. All right, so if I click on the event messages by time, we did not have these two tabs in the previous tank filling scenario. The reason why these tabs are here is because I have events that have activated. So this tells me that these two valves closed at a certain time, 32 minutes and 113.5 minutes. So what happened was the liquid height for the respective tanks would have gotten to be the certain level to cause these two valves to close. So valve B, this is the one that closes first. After that happens, the flow then gets diverted to through valve A and valve C. And then the second valve that closes is valve C. And then after that, all of the flow is diverted up to the top tank right here. So first question is, how do the tank liquid heights change over time? Well, if I go to my graph results tab, I can simply reload the same graph that I showed before. And if you look at this, these shapes, oops, I didn't actually double click it well enough. These shapes are actually different than what we saw in the previous scenario. So my yellow curve here, this is the valve that closes first. And as you can see, the slopes of the other two tanks changes very slightly, because that's where additional flow is now being diverted to the other two tanks. As we march forward in time, the second tank, which is the blue curve here for going through valve C on the far right, this changes right here at about 118 minutes or whatever it was. And so that, I'm sorry, it's the green curve, not the blue curve. And so the green curve, I've leveled off, my valve is closed. I have no more flow spilling over in those two tanks because the valve is closed. That's good. And now all the flow is going through the tank on valve A on the left. Now, when do all of the valves close? Well, all you would have to do is run your simulation for a longer period of time. So in this scenario here, I changed my transient simulation to 200 minutes. So that's actually just a little bit more than 3 hours. So I'm going to go ahead and run this. While that is running, I'm going to open up a spreadsheet because in this example, I set up a Excel export to spit out what the how the liquid surface elevations for each of the tanks change during my analysis. And so these are the final output results for my liquid heights. You're going to see when I start getting into Impulse why I needed this information. I just wanted to pull that up while my XTS simulation was running, and it's almost done. Perfect. All right, so let's take a look at the output. If we go to the output window, we can see that we have some cautions again, which is not a real issue to be concerned about. But if I go to my event messages by time, this tells me exactly when each of the valves close. Valve B closes first at 32 minutes. Valve C closes second at 113.5. Valve A closes third at 187.5. So that's when my three valves close. If I go to my graph results window, I can then plot this graph here, which is my 200-minute graph. So this very clearly tells me when each of these tanks are not receiving any more flow. So the valve A or the valve B in the middle shuts off first, valve C on the right shuts off second, and then finally valve A on the left shuts off third, and now I have no more flow. So this is what I wanted to figure out, is when all of the different valves close. There are some other parameters that I plotted. I also plotted how the pressures change at the valve inlets. I'm not going to go into too much detail, but this gives you some information about essentially what the deadhead pressure would look like once your valves are closed at each of those points, and they build up over time. And then I also needed liquid surface elevations. And my liquid surface elevations, I created this graph to set up my Excel export, which is defined accordingly. I'm transferring all of my liquid surface elevations. That's not just the liquid height, it's the actual true elevation of the liquid surface level. And I'm sending that to this spreadsheet. The reason why is because the AFT Fathom XTS analysis allowed me to figure out the answers to my questions of: when do the valves close? Do any of the tanks overfill? How does the pump operation change over time? I'm looking at what's going on in the entire system over a really long period of time. So what I would want to use AFT Impulse for is for the application of, hey, I know that this particular valve closes at 33 minutes or whatever it was, and it's closing in 30 seconds. So that's a really fast valve closure. When this valve closes, the flow rate in this pipe is going to stop. I'm going to have a pressure surge that's going to pass throughout the system. How does that pressure surge change in the rest of the piping system? Do I have pressures that get to be above the pressure ratings of the pipes? Is there any damage that I need to be worried about? And so I'm not looking at a 2-hour simulation. What I want to look at is, at this exact instantaneous moment when this valve closes, what's going on over a short period of time. So that's where we'll get into start talking about AFT Impulse here now. Okay, so for AFT Impulse, I'm not going to, I already did import the AFT Fathom model into Impulse. So this process here on this slide illustrates how you go about the process of importing a Fathom model into Impulse. To import it, you simply run Impulse, then go to File, Open, browse to the folder where your Fathom model is located, change the file type to all, and then select the Fathom model you want to open, and then that'll open it up right on Impulse. Super, super easy. And this is one of the biggest benefits of our software, is each of our products shares the same interface. So if you learn Fathom, you know how to use Impulse or Arrow. In addition to that, each of our AFT products allows you to transfer a AFT model from one AFT application to another. You could also take an AFT Impulse model into Fathom. The process is the same, but it's just reversed for the file type. Really easy. Mostly all of the data imported into Impulse is really simple. Some data might get slightly modified. An example is elbow junctions convert to general components with a K factor in Impulse. There's a reason for why that happens, and I'm not going to get into that right now, but just know that 99% of your data is going to import just fine. There just might be a couple things that you need to clean up super quickly. Another thing that Impulse will try to do is to combine pipes to simplify the model upon import. That's a really good idea, and if you watch one of our video tutorials on pipe sectioning, then that'll illustrate why you'd want to combine your pipes. That's outside the scope of today's webinar. One of our videos illustrates that you can find on our website. But it's probably a better idea to combine the pipes in a child scenario. So once your model is imported, you just need to set up the transients. So here's where you would be able to use Fathom XTS and Impulse together. And this will clear up where the XTS simulation stops and where the Impulse simulation would start. the impulse analysis begins when my valves have closed. So the start time is going to be whenever the tanks are filled to the various levels when a certain valve closes. So if you can picture this, in a certain scenario, the very first valve that closed was valve B. It closed at 32 minutes. So this is the valve that closes. So at 32 minutes, I have a certain liquid height in my supply tank, and then certain liquid heights in each of my discharge tanks, which are different from the initial conditions. So this is where I have my spreadsheet where I took the data from, where I took the data from Fathom XTS and I spit it out. This is all the raw data. And what I did was I simply scrolled down to each of the different time frames. So this is 32 minutes. This is when valve B closes first. And then if I scroll down further, the next one at 113.5 minutes, this is when valve C closes second. So the summary data is this information right here. So these are actually my starting conditions for the supply tank as well as each of the discharge tanks at the time when valve B closes. So if I go back into AFT Impulse now, here's the scenario that I'm going to examine first. Valve B closes. So this is going to be at the 32-minute mark. At 32 minutes, I have a certain supply tank liquid height, and all I did was I just took my spreadsheet value at 32 minutes, and then I plugged in each of these values. So, for example, I've got 46.6 feet for my supply tank. So if I open this guy up right here, I've got 46.6 feet for my liquid surface elevation in the supply tank. Then I did the same thing for my discharge tanks accordingly. And I set up my transient on the valve. The thing to note here is that this valve is a simple transient than it was in XTS. Here, I don't need to set a single event because I know that my criteria is already met. I know that my tank height is already too high, so this is my start time. At time 0, this is when my liquid heights are where they are, and that's exactly when my valve begins closing. Now, incidentally, the other two valves are still open, so I do not have transient set for those two valves yet. Now, for the sake of time, I already ran the simulation in Impulse because it takes a little bit of time and I don't want to have to rerun the model for my Impulse analysis. The specific questions that I had was for AFT Impulse in this analysis. What happens when the valve closes? What are the system pressures? Is there cavitation? How does the pressure of the valves change? How does it compare with XTS, etc.? So those are the questions I'm wanting to ask here. So if I go to the output tab where I already have results, I have data that looks similar to XTS with Fathom. In Impulse, the tabular data is a lot less useful. And when you're doing a waterhammer simulation, it's all about graphing. Graphing is the best way to be able to examine your results. So that's where I'm going to spend the majority of my time. This tells me that I have cavitation. That's a whole separate discussion, but we'll see what's going on there. It's telling me I've got cavitation in pipe 8 at the outlet. All right. So where's pipe 8? I'm sorry, it's actually at the inlet. That's this pipe right here. So I have cavitation going on. Well, what does that look like? Well, the first thing that I did was I right-clicked on this valve, and I clicked on Generate Transient Graph for the immediate connected pipes. So I want to look at the valve inlet pressure and outlet pressure, and that's the static pressure. So I already generated that graph. After I created the graph, what I did was I added on the vapor pressure because comparing pressure, static pressure And vapor volume is really easy. So that's actually this graph that I've already fully defined. It's this graph list item, so I've already prepared it for myself. So there's a lot going on here. Let's break this down. I'm going to turn all of these off. What is happening at the inlet of the valve? Well, that would be the outlet of pipe P4 for pressure and then vapor volume. So what this is telling me is because the vapor volume is at 0 upstream of the valve, I don't have any cavitation upstream of the valve, so that's good. So what this says here is when my valve closes, I have a spike at the pressure on the upstream side of the valve that gets up to a certain level. That pressure is about 230 psia, so right around 230. So I could go into Fathom and compare that. If I go to the graph results, it's actually a different scenario. I want to look at what the valve pressures are. There's an important reason why I'm showing you this. It's because XTS does not do the waterhammer, does not do surge. So if I plot the pressure at the valve inlets when the valves close, we'll break this down. Here's the valve that closes first is for pipe P5. So if I look at pipe P5, when this valve closes, it's telling me that my initial pressure before valve closure is about 189 psi. Once that valve is closed, it's telling me that it's 197, and as I'm pumping against a closed valve, the deadhead for that valve would be about 198.5 psi. So this is where AFT Fathom XTS is not going to tell you what's really going on at that valve. This is where you have to use impulse because there's a surge event going on when that valve closes, and XTS is not going to pick that up. So if I zoom in here, when my valve closes right at 30 seconds, my pressure surges up to 233 psi. That's a lot higher than what XTS predicted. So this is why you need to use impulse, is because it will track what's going on for really, really fast transients. Now, let me zoom back out and let's look at the downstream side of the valve. The downstream side of the valve, as you can see, has a lot more noise going on. What's going on here is the pressure immediately drops downstream of the valve, and this green curve, that's vapor volume. So when my pressure drops, I hit vapor pressure, I start to cavitate. So I have a vapor bubble that forms. It's basically a balloon inside of the pipe. And once that vapor volume drops back down to 0, that's when my balloon pops. If I zoom into that time frame, when the balloon pops, here's our rangefinder, I have a major pressure surge right on that valve, and it's a very high pressure spike. So this causes a lot of issues with cavitation. So yes, there is cavitation going on downstream of the valve. That's a problem that you'll want to address so you do not damage your pipes. Your pressure spikes can be much, much higher when you have cavitation versus when you don't have cavitation. And that's what you're going to need to use impulse for. Maybe you need to put in a gas accumulator or a surge tank downstream of the valve to absorb those pressure surges. So that's my first scenario. Second scenario is valve B is already closed, and I want to look at what happens to the valve C closure. So this is at 113.5 minutes. So my valve B is already closed. What I've done is I've deleted the downstream pipe and tank because this is a closed valve. So that might as well just be a dead end. I've simplified my model for myself. So I used the dead end junction to represent my closed valve because this is a reflecting point for when I have that water hammer hit. So now I'm doing my transient on this valve because this is the one that I know will close second. So what I had to do for this scenario here, the second one, is I had to go back into my spreadsheet and I had to update my liquid levels. So these are the new liquid levels that I need for this scenario. I've already done that, and those liquid levels are updated accordingly. So with running this scenario where this is the valve that's closing, let's take a look at the results. I've also got cavitation going on, which tells me right here. So let's look at the same thing that we looked at before. What are the pressures at the valve? Well, I already created that graph. So if I double click on the pressure and vapor volume at valve C, it looks very similar to what it did before. Getting the dreaded, there we go. Just took a little bit of time. And so this is very similar to the initial pressure surge. Again, I'm going to break this down a little bit. I'm going to turn off a couple of these graphs. Here's what's going on at the inlet of the valve C. As you can see, my pressure spikes up. I get to a certain valve, and then there's a little bit of a noise here. So that's a very realistic pressure oscillation. So if I use my rangefinder to zoom in on a shorter time frame like this, this is what's going on at that valve. So after my valve B is already closed, this is the next valve that closes, and that's how high my pressure gets, which is about the same value, 237 psi. And then afterwards, I have some more oscillatory behavior, which just, that's going to be whatever it is based upon my piping configuration. And maybe there's some resonance, and maybe that might be an issue, but that's what the results of the valve are. Now, one thing that you might want to consider doing is an animation. So what I might want to look at is how the pressure changes along a flow path for this part of the system. So if I select these pipes on the workspace, I can go to my graph results window and I can turn on another graph tab, and under my profile plot, just click workspace. When you click on workspace, it'll automatically check the boxes, the pumps or the pipes that are already selected for you. So here I'm going to animate how the pressure changes throughout that part of the system. So I'm going to modify the axes a little bit. This will be 2,300 feet, and I'll do 250 foot lengths. This button right here turns on my labels for my where my components are. So here's my valve. This is where my valve is. It's at that location right there. So if I ramp up my time speed and I play the animation, as you can see here, the time ticker is moving forward. Again, that valve, which is right here, takes 30 seconds to close. What you see here is that as this valve is actually closing, nothing really happens until the very, very end of the valve closure. So if I go in and pause my animation, I can scroll forward in time right to about here. So now if I go to 28 seconds and slow it down a little bit, this is now when you finally start to see some stuff happening. So that valve is closing, and then pretty soon, once the valve is closed, you'll see how the pressure oscillates throughout the system. So what you're looking at down here is you're seeing how that cavitation behavior after the valve is causing problems, and then you have a major pressure spike. And so this is definitely a big issue. You might need to put some surge suppression equipment downstream of the valve to help mitigate or prevent the cavitation behavior. But if we care about what, or we do, we care about what's going on upstream of the valve, I can shorten this to this area here, and we can look at the same sort of thing. So this is before the valve is closed, And then once the valve is closed, we can better get a picture of what's going on in the upstream part of the system. So this is how one of the best ways to examine your results for a water hammer analysis and impulse is by doing these types of animations. If I pause this and use my default speed, you can see how the pressure is fluctuating a little bit at the inlet of that valve. And so this is where your concern is when you need to use AFT Impulse. How high does this pressure get? Is it oscillating between very large envelopes of pressure? That's what you need to know. XTS will not do that. Impulse will. My last scenario was for the final valve closure. So valve A, similar to before, I know that valve B and C are already closed, so those are dead ends. Valve A is the last one that's closing, and yes, I already went into my spreadsheet and I got the appropriate liquid surface elevation values to update my tanks accordingly. And when I go back into Impulse, if I after I rerun my simulation here and look at the output, I've got some bigger issues. What this warning message is telling me is that I've got backwards flow through a pump. Well, if you think of a pump curve, just like this, what is the pump head when you start to experience reverse flow? So as your flow drops below zero and your flow rate starts going backwards, what's the pump prediction? Well, it's hard to say. So just using the pump curve alone is not good enough to tell you what's really going to happen. That's a 4-quadrant curve, and that's a discussion for another time. But what we can see is how our pump flow rate changes. So if I go to my graph results window, I want to plot my pump flow rate to find out when do I start having that reverse flow. Well, the answer is it turns out that your pump starts to experience reverse flow pretty much immediately after valve A is closed. And so if I was to zoom in into that particular time frame right here around 30 seconds, my valve closes and then the flow rate drops off very quickly, and then I start to have this very chaotic behavior of the flow rate through the pump. What this means is that the results are going haywire and may not be as accurately predicted. So if I open up a new graph tab and I plot the pressure at valve A, the graph that you see here goes nuts. And this may or may not be realistic depending on how much cavitation you've got, which you can see you've got a lot of cavitation going on, and my pump is just not providing accurate predictions. The last scenario would be, okay, well, I certainly don't want to pump against a closed valve. So the scenario that I would create after this one would be when this valve right here closes, let's put a pump trip on the pump. That way I'm not discharging against closed valves anymore. And so that's another application question of what you would use Impulse for versus Fathom with the XTS module is a pump trip once a valve is closed. Anyway, I hope that this helps you get a really good feel for the two different tools that are available for doing transient modeling. So now, whenever you think of the word transient analysis, it means two different things, and it's all about understanding which type of application you're looking at, long-term or short-term, Fathom XTS or Impulse. And so in my presentation here, I've included some direct links to some incredibly useful Impulse resources. Definitely be sure that you check these out. That way they will help you start to get a handle on how to use AFT Impulse properly. There's our quick start video, several additional video tutorials. Earlier when I talked about combining pipes when you import a Fathom model into Impulse, that's the pipe sectioning video that I was talking about. That's very important to read. And then there are some additional Impulse webinars that are really useful that you can find there. Anyway, thank you all very much for your time and for listening into the re-recorded version of today's webinar. Sorry again for the technical difficulties earlier this morning, but there you have it. If anyone has questions, please do not hesitate to contact us. You can email me directly and I'll be able to send you my presentation. If you want to try out either Fathom or the XTS module or Impulse, and you don't already have that software, let me know and I'll be happy to set you up with an evaluation. We can get you quotes. If you are outside of the United States, then contact your local channel partner and they'll be able to help you the same. Thank you very much, everyone. Take care and have a wonderful day.